Schnoebelen of the Laboratory for Specification and Verification at Recherche, who will speak on well-quasi-orderings.
Okay, so thanks a million. I'm very happy to have been invited to give this talk in front of this audience. So I'm not a set theorist myself, and I must say that some time have been lost during the previous talks and probably some of the next talks. I'm a computer scientist. My field is program verification. And it turns out that I use well-quasi-orderings for this. So usually the talks I give, my colleagues have to explain to them what are these well-quasi-orderings and what to do with them. And of course they think we're half crazy. And here I guess it will be, I won't have to explain to you. In fact, the definition, I've removed it from I assume that everyone knows the definition. And I will spend more time describing, so probably what for you will be an application. And so this is joint work with Sylvain Schmitz, who's in the room here. Okay, so program verification. So I'm talking about automatic program verification. So the goal is to take any kind of computer programs and to prove that they are correct. By correct, we mean they have no bugs, they behave as expected. Of course, all this has to be defined. And the main point is you want to do this automatically. So, the programmer, in an ideal world, would just write his program and then press a button and ask, so tell me that this program is correct, that it has no bugs, and then he would get a certificate, and he would be happy with that. So this area was pioneered by Amir Pnoueli, also Clark, Emerson, Joseph Sifakis. This was in the early 90s. So I'm very happy to mention their name because all four of them received the Turing Prize for their contribution to the field. So the Turing Prize is the highest prize for computer scientists. And I'm mentioning this especially since Alan Turing was a Cambridge student, so it seems like a good point to mention. This area is now very active. Already in the early 90s, it was used by companies like Intel or Airbus or things like that. And maybe something that is hard to explain outside our field, where we have by our field, I mean, I include you, so where we are logicians, is that we are always developing new models and new theories, and the point is that we need to find the best compromise between expressive power and tractability, and of course you want just the required expressive power without breaking the tractability. Okay, so well-quasi-ordering in this area, it turns out that there is a generic family of model. We call them well-structured transition systems. I could also say well-quasi-ordered systems. They were invented already 30 years ago by Finkel, so not Olivier Finkel at the back of this room, but another Finkel. In fact, you can find Finkels everywhere. This was really developed 10 years later by Parosh Abdullah and Ben Johnson in Sweden, and then by Finkel and myself. I'll show you some example. It was used with at beginning with basic data structures like counters, queues, but a feature that it was unexpected for me when I started this research like 20 years ago, is that it is still very thriving, and every year we see new group adopting this model, And with new instances, so they use a new, maybe not new well-quasi-orderings, because, you know, with I don't know, with the graph minor theorem, probably we have covered all the quasi-orderings that will be used in computer science, but the way they used it or the application they have, I see new things every year. And what I want to mention a bit today is some recent developments where I've been involved with Sylvain. It's about the complexity of or the expressive power of this well-structured system. So this is something that in the beginning, so in the 1980s, 1990, people thought was, you know, completely impossible to attack. It turns out that using tools from proof theory, from ordinal analysis, we can say things about the complexity. Okay, so the outline of my talk would be so some basic examples, just so that you understand what I'm talking about. I will present two verification algorithms, so how we can answer automatically whether our programs are correct or not in this WSTS framework. And then, depending on what time is left, I will be brief or long on the tools we use for complexity. Okay, the basics. So I will start with this example. This is a channel system. So the kind of model that we like to use. I'll show you another example later. So you have two machines, one here, so let's call it the sender, and one here, let's call it the receiver. And they are models for maybe what is happening in your computer when the computer is connecting to the internet provider and they're negotiating something. Or maybe when a secret shared key has to be exchanged. So this kind of system we are modeling, and basically, so it has to be just schematic so that it can fit on the slide. But basically, this one here has two states, and when it's in P1, it can move to P2 by sending a message 1, and the 1 will be put in the queue behind these two. And this one here can read the messages. For example, this loop, so the question mark means I read. So with this loop, it will be able to read the zeros, and then, so maybe it will be stuck because there will be a 1 in front, and nothing can, I cannot do anything with the 1. So, yeah, the channels are unbounded. This is asynchronous communication. The messages that are sent, in fact, this is just a model, and in the real life, the messages are much more complex. Here, I've just written the priority of these messages. So, really, there is a message with priority 0, a message with priority 0, a message with priority 1, and for this protocol, I don't care about what we do with the messages themselves. I just care about the logic of exchanging them and ending the priorities. So the way this behaves is I have a current configuration, so I see from above the whole state of my system, so local state of sender, local state of receiver, content of channel 1. So I write the head of a channel, you know, like in English we write from left to right, so the head of a channel is there, and this one I will read backward, this one I will read this way, and content of second channel. And by doing this transition, as I explained, you know, I will move to this new configuration, and this is the dynamic of this kind of steps when you chain the steps that I'm interested in. And of course, it's non-deterministic because here the first process did an action, but it could have been the second one, and they don't communicate except through this channel, but otherwise their relative speed, what is one step for them, is completely independent of what the other is doing at the other end. So I said that these numbers encode the priority of messages because in this system I have another kind of step. It's possible this is something that happened in this step. It's possible for one message, so here the one here, to supersede the message that is in front of it on condition that the message in front of it is not of higher priority. So this is what happened during this step. This 0 has been, I don't know, kicked out of the queue by this one that is just after it. And this is a model of what can happen in a real network. So a real network like the internet, they have no guarantee of transmitting messages. They're allowed to drop some. And in some situation, you're allowed to drop the lower priority messages in order for the higher priority message to not be blocked. So this is what we model here. And I won't tell you more about this example before, later when I'll come back and tell more about it. Okay.
Excuse me,
Sure.
in your example there, it didn't just look like it was being superseded, it was being dropped.
Yeah, dropped, yeah. So maybe my English is... so you don't go in front of the message in the queue, you just kick it out. So I should say, what should I say instead of supersede? I should say overcome.
Delete.
Yeah, delete. Yeah, okay. Take its place. Take its place. Yeah. So this is what happened.
Take place.
Yeah. So in general, this system, the system, the thing I've put on the slide is a program, but what I'm interested in is the behavior. And the behavior is all this configuration that are obtained from the program and how you can move from one configuration to the next. And what I'm interested in is a question about the path in this transition system, in this graph, let's say, infinite graph, because my channels are unbounded. So two main questions I'm interested in are question we call safety. So I have some set of initial configuration, some set of bad configuration, and I want to prove that there are no paths from the initial configuration to the bad configuration. And for example, this would be proving that division by zero never occurs, or that situation where the receiver is stuck because there is nothing it can do. This never occurs. And also another kind of questions are inevitability. So now I have some good set of configuration, and I want to prove that all maximal paths from the initial configurations eventually visit the good states. So by eventually, I mean that maybe the path has not yet visited the good state, but if I make the path longer, so if I wait and I let my program run longer, for a longer time, eventually the good property will happen. And typical example is termination. So the good state will be the terminated state. So when I want to prove that my system terminates, this is an inevitability property. Okay, I show you another example, and this one we will analyze a bit in more detail. So there's a broadcast protocol. Again, another Finkel. They are called also population protocol. So again, it's a model for dynamic, for distributed systems, but this time they are dynamic, and by dynamic we mean that the number of participants is not fixed and can increase. So here, let's see what happened. I've not depicted communication channels because messages are not buffered. Now this is a synchronous communication. So everyone is running this little program. So when I'm in a given local state, I can do one of these actions. So for example, a configuration of my system will list for every participant what is its current state. So for example, here I have 3 participants. 2 of them are in this state and 1 is in this R state. So what can I do when I'm in the C state? I can take this spawn action and it will not only change my local state, but it will create a new process. This is why I have two arrows. So this is how one process will become two. So the number of participants can grow dynamically. So this would be a step of my system. So I have two participants in state C, and after the spawn, I just have one left in the state C, but now I have two in state A. Like, you know, this is these two arrows, this is what they're explaining. It's possible to do another spawn step, and now I have four participants in state A, and nobody is in state C anymore. I have these other kind of actions. So these are message sending. So all these messages here, we see they are broadcast messages. So what happens here? Here I have someone in state Q, and sends the M broadcast the M message. So when it does this, it moves to this bottom state, but everyone who can receive the M hears it. So this is a model for you know, the protocol that is run around an antenna where different machines are listening to the server, to the phone server. So it sends this M, and everyone who's in state A and can listen to M will move. So this is why the Q here become bottom, but the 4 A's become 4 C's. And if there is other processes that are in a state where you cannot hear M, this means if I hear M, I don't do anything. I stay in my current state. And here you have another example where the R, so the R here couldn't hear M, so it stays in state R. But now it can broadcast a D, it becomes C, and all 4 C's will listen to the D and will move to Q. So this is the kind of dynamics I have in this system. I also have rendezvous exchanges where just two processes synchronize and move, but it's not displayed on this example. So I can prove that this protocol terminates. So it has no infinite runs, and the way to do it with a configuration, I will write it this way. So N1 R's, N2 Q's, N3 C's, and the rest I don't care. And in any step, this tripole, N1, N2, N3, decrease in the lexicographic ordering. So this is easy to see. You take any, you know, it's a case analysis, you take any step. So for example, this spawn here, N3 will decrease, N2, N1 are unchanged, and I have more A's, but I don't care about that. If I do this D, R1 is decreased, so maybe there will be more N2, but in the lexicographic ordering, decreasing N1 wins. And we know that the lexicographic ordering of the tripole of natural numbers is well founded, so I cannot have an infinite sequence of steps because, you know, this is bound to reach a bottom, and you cannot go down anymore. So by the way, this kind of proof, this is the pattern for all termination proofs. And already in 1949, Alan Turing proved termination of a program by using this kind of lexicographic ordering. This was completely unnoticed at the time, and it was this paper by Turing was rediscovered later when he became famous. The technique is you invent a well-founded measure, and you prove that it decreases with every step. So this part proving that it decreases with every step, this is a local step. You know, you just have an arbitrary configuration, and you just do a local change for you know, just one little computational step. And usually, this part is easy. What is hard is to invent the well-founded measure. And in fact, it's not only hard; it's impossible. There are many systems where the measure exists you know, in the universe of mathematics, but you cannot write it down with the formula. So just inventing it is not enough. Of course, you have to write it down if you want to prove something. Just to give you an example, you know this. So I've been told that you can use. So this I don't know. No batteries in it, or it works just like that. Okay. So I've seen people. So this board must be working because I've seen people using it in previous day. So if you look at the Collatz conjecture, where you start, you know, if you have, I'm sorry, if you have a number that is even, you go to half of n if n is even, and otherwise you go to 3n plus 1 until you reach 1. So we don't know if this terminates. This is a very simple program. We don't know if it terminates. It's a major open problem in mathematics. And of course, if it terminates, there is a measure. You know, this will define, this transformation will define a well-founded ordering on the numbers. Maybe it's not an ordering that I can write down, you know, comprehensively. So it can be very hard to invent this measure. And another difficulty is that so when I write a program, of course I have an idea of why the program should terminate, and I have an idea of what would be the measure that would be used to prove termination. But if I do automated verification, it's because I know that programs have bugs. So maybe I know why the program should terminate, but when I write down the program, what I write is a little bit different from what I had in mind. Just a typo. You know, it happens when you write programs. And so the thing that I want to analyze, the thing that I want to prove has nothing to do with my ID. You know, you take a program, you make a typo, and then it has nothing to do. So it's really very hard to find these measures. Okay. So for this one, for this example, okay, it's easy, I could do it. But how would I do this in general? Well, it turns out that broadcast protocol, they are well-behaved. So what do I mean by well-behaved? So if I order the configuration not with the lexicographic ordering, but with this multi-set inclusion, now my steps are monotonic. What do I mean? I mean that if from configuration S I can go to configuration T, and if S prime is larger than S in this ordering, then from S prime I can move to some T prime that is larger than T. Okay? So how do you see this? Well, you can prove it by a simple case analysis. You look at you know, what is every kind of steps possible. So for example, if I'm in S and I do a spawn step, so I will remove one process from this configuration and put 2 there. Now if T is larger, I can do the same thing, take 1 here, remove it, put 2 there, and the result will be larger than T. And you can do this with the different kind of moves that are allowed, and you can prove this property that the steps are monotonic. And one last ingredient is that this ordering is well-quasi-ordered. So here I will give a definition just for the record, meaning well-founded and no infinite antichains. So when we have these 2 properties, so we have an ordering such that steps are monotonic and the ordering is well-quasi-ordering. So we say that our systems are well-structured, and for these systems, termination and safety are decidable, meaning that there is a method that will always tell me if my system terminates or not. By the way, this is something important I forgot to say. When I say that it's hard to come up with termination proof, and in fact it's impossible. I was only talking about programs that terminate. Of course, if my program doesn't terminate, it's even harder to come up with a termination proof, of course. So by this decidability result, I mean that not only I will find a proof for every terminating system automatically, but I will also find a proof for the non-terminating ones. And this is a different kind of proof. Okay, so this model now, well, I can do the same trick with it. So when you have this channel content, so let's write it this way, I will use this arrow to mean you move from u to u prime by one overtaking step. So pi has been dropped because pi plus 1 is higher or equal priority. And so this is what happened here in this step. And I take the transitive closure of this relation in the other way, because of course when I move from u to u prime is shorter. So for an ordering here, I should take the opposite. And I just extend it from one channel content to a full configuration, but basically is just the transitive closure of the preceding. So now my steps are monotonic, because if S prime is above S, this means that just by superseding steps, S prime can become S. And so now, when S prime has become S, it's possible to do the same step here and reach, so I don't need to reach a T prime that is above T, just I can reach T exactly. And since this ordering is a well-quasi-ordering, I have my ingredients, you know, a well-quasi-ordering among my configuration, monotonic steps, and so my priority channel systems are well structured. And again, I will apply this theorem that I can decide termination and safety. And this kind of models with this kind of property, we have dozens of them. So now what I will do is I will explain how we decide termination and safety, because after telling you that it's hard and impossible in general, how do we do that? It's very simple. It's a generic algorithm, so the algorithm, they know nothing about priority or broadcast protocol, or it's generic algorithm. So for termination, I have this lemma, finite witnesses for infinite runs. So my system has an infinite run starting from some initial configuration, if and only if it has a finite run that is a good sequence. And recall that a good sequence is a sequence with an increasing pair. And well-quasi-ordering tell me that all infinite sequences are good. This is the definition. So I'll try to prove this. I don't know how you do reset on the board, so I'll use another one. I'll try to prove this lemma. So if I have an infinite run, so this is it. Okay, well quasi-ordering, this sequence is good. So there is, I don't know, Si smaller than Sj here to the right. So if I stop here, I have my finite good run. So this part is the trivial part. And the other one, the other direction is very easy. So if I have a finite good run, so something finite here, but I have Si smaller than Sj for I to the left of J. So from Si, I can go to Si plus 1. And good run means that Sj is larger. So now monotonicity tell me that this step can be mimicked here. And I can go to some Sj plus 1. Maybe it's not the Sj plus 1 that is in my sequence, so it's another one. To some Sj plus 1 that is larger. And from S1 plus 1, I could go to Si plus 2. So again, I can mimic. And eventually, I will reach something that is larger than Sj, and I can iterate this, mimicking the previous steps using the monotonicity property, and I can show you that there is an infinite run. I don't need to list it completely, just the finite part with this increasing pair just is a witness that there is a possible infinite run. So, yeah, I had a backup, so the proof is written here. I was not sure I could do it on the board, so I had the backup ready. So this is the same argument, but the corollary is that I can decide termination just by enumerating all finite runs. So when I do this enumeration, if at some point I meet an increasing pair, I can stop. And even if I just have explored a finite prefix, I know that there is an infinite run. And if all runs are bad, well, Koenig's lemma, eventually I will have exhausted all the runs. When I say Koenig's lemma, it's because I have this assumption that I didn't mention, but my systems may be non-deterministic, but they are finitely branching. So from any given configuration, I can reach only finitely many configurations in one step. And so this very basic idea works, and it can be extended to prove more than termination, but it's just the same idea. When I say this very basic idea, it's because it's the most nice thing of trying to explore all the runs of my system. But this will, and usually this never works usually. But here I have this criterion that if I meet a good sequence, I can stop, and this will happen, or I will eventually exhaust all the runs. Okay, other algorithm now for deciding safety. So for this talk, I will use coverability, which is almost the same as safety. So the question I'm interested in is, so I have my system, I have some initial state, some target state t, and I want to know, is there a run that, starting from initial state, eventually reach some Sn that covers t? Okay, so is it possible that eventually I will cover t? So maybe t is division by 0, and I would like to have a negative answer. So having such a run, it's equivalent to having what I call a pseudo run. So a pseudo run, it's a sequence of states just like this one, but instead of having a step between Si and Si plus 1, I just want that from Si I have a step that covers Si plus 1. So this would be the picture of a pseudo run. And I'm interested in a minimal pseudo run. So a pseudo run is minimal if the Si in every step is the smallest way of covering Si plus 1, the next state in the run. And now I have this lemma with the finite witnesses. So the question I'm interested in, there is a run or a pseudo run. You know, runs are a special case of pseudo runs covering T. If and only if there is a minimal one that is bad, a bad sequence when I write it from right to left. So again, this is very easy to prove. So let me try that. Oh, this is the way you reset the board. Okay. So great technology. So, of course, if I have a run that eventually cover T, if this run is not minimal, I can take any, so let's say I have Sn minus 1 and Sn minus 1 is not minimal. I can replace it by something smaller, and now I just have in my run, I just have a step, I reach something, I go down, and this will be the by decreasing this thing, I will eventually get something minimal if I decrease all of them. I can go to minimal because my ordering is well founded. And if this minimal run is not bad when I look at it from the right, this means that there is some Si here that is larger than some Sj to the right. But if Si is larger than some Sj, I can just cut out all the middle, put Sj below Si, and I have a shorter run. And of course, I cannot get shorter pseudo runs, forever. Eventually, I will have shortest length, and with all the state minimal. So, of course, if there is a pseudo run, there is a minimal one, and if there is a minimal one, in particular, there is one, so the other implication is obvious. And because I have this criterion that I look for bad sequences, again, I can do this exhaustive enumeration. So I can decide coverability by enumerating all pseudo run. I have to start from T. So this is a feature, strange feature of this algorithm. So you have to start from the right. It doesn't work if you start from the initial configuration. And I just look for bad pseudo runs. When it's good, I don't extend the branch anymore. So this again will give me a tree with only finite branches by the well-quasi-ordering property. And this condition of looking for minimal predecessor, this will give me the finite branching. So when it's something it's a bit tricky to picture, but when I want to explore this run, so I start from a configuration and I have to find out every configuration that can go to this configuration in one step. So this is kind of solving an equation, from what configuration could I be starting to get to this current configuration. And it can happen that you have infinitely many solutions. In particular, if I have an operation like, put 0 in x, and I want to reach a state where x equals 0, from what configuration can I start? Well, any value for x is possible because the step will be put 0 in x. So looking at the minimal one, this is what will give me finite branching in this exploration. And I need this for Koenig's lemma to apply and give me termination. So enumerating predecessor is a bit trickier than enumerating successors. Of course, you have to do this for the model at hand. For my priority channel system, for my broadcast protocol, for all the models that I use, this is something that we can do very easily, usually. But it's an ingredient that you need. It's outside the algorithm. Okay. So now, complexity. I'll start with the bounds. I'll go back to these examples. So we saw that it terminates. It turns out that it can take time to terminate. And for example, it's possible if I start with n processes in state C and one in Q, they can do the spawn thing n times, and then I will have 2n A's, 1 Q. Now if Q does an M, the 2n A's will go there, and now I have double number of C's from what I started with. This used 1 Q. Of course, if I had n Q's, I can do this n time, and so in the end I will have, I started with 1 C, now I have 2 2vn C's. And I have exhausted all my Q's, but since I was smart and I had 1 R also to begin with, now I do this D, and all all the C's will become Q's. And the R will give me another C1. So I can replace Q by n Q's by 2 to the n Q's, just consuming one R. And if I start now with n R's, so I can get how many Q's? Tower n, so tower is 2 to the 2 to the 2 n times. So something that is non-elementary. So this protocol terminates. We saw this with the lexicographic ordering. When I try to exhaust all the runs, I will have runs that are of non-elementary length or depending on the size of the initial configuration. But if I start from this, I will have runs of non-elementary length and some other runs. This is just, I'm just talking here, I'm just showing you one branch. So the naive termination algorithm that I've shown can take a long time to answer.
Now, what is elementary?
Elementary mean finite combination of multiplication, addition, exponent. So it includes everything that is exponential, double exponential, triple exponential, but you know, fixed level of exponential. And here the tower, the level of exponentiation depends on n, so it's not fixed. So this is why we say non-elementary. I don't know if maybe this is a jargon from algorithm analysis. Okay, so to give up a bound to this, we have to use the fast-growing hierarchy. So I guess that most people here are familiar. This is the part when I talk to computer scientists where I have to explain, give example, and where they think I'm crazy. So you have this function of natural numbers that are obtained by iterating the precedent function. So f, the successor function f alpha plus 1 is just f alpha, but how many times? Well, x time, x plus 1, so that it will be at least one time. And if I want to know what is f omega of x, well, I will use x to know which f alpha to apply. So it's a kind of diagonalization of all the f k's for finite k's. So f omega will pick one value from f1, one from f2, and so on. So what it gives is that, so the symbols mean behave like. It doesn't mean that eventually the limit of the ratio is 1 like they do in mathematics. It's a weaker notion of being equivalent. So already f3 will be something like tower, and this f omega is like the Ackermann function. It's the first f alpha that is not primitive recursive. All the previous one, of course, are primitive recursive, and the hierarchy goes on after omega. I can apply this to compute f omega plus 1, f omega plus 2, and at any limit ordinals, I will use x to pick the previous index for which I want the function. So for this I need, for every limit ordinal, I need to have fixed a sequence of approximants. There are standard definitions for this. In the end, I will define this class of functions. So I say I will define. This has been defined by Weiner. So Grigorchik first for the finite levels, and then Stanley Weiner and so on. So this class of function, all functions that are computable in time. So f alpha may be nested a finite number of times. This class of function that is very robust. By very robust, I mean that it does not depend too much on how I pick the fundamental sequence for my limit ordinals. Here, if I take alpha plus 1 or, x plus 1 or x, it won't be so important when I close with this kind of construction. So basically, this family F3 will already have non-elementary function but it will be a finite number of it will be bounded by a finite number of iterating tower, a fixed number of iterating tower, and F2 already will have all the elementary functions. Okay, so when I looked at my termination algorithm, the basic question is how long can a bad sequence be, because I'm exploring all of them. So it will be the longest branch in the tree, and by well-quasi-ordering theory, I only know that the bad sequences are finite. And it turns out that bad sequences can be arbitrarily long. So if I look at natural number, by starting from very high, I can make long sequence. You tell me how long you want the sequence to be, and I tell you, okay, starting from that number, it will be long. And if I have tuples of more than one element, I can start from some small element. At some point, I will jump, and I can do this several times. So I don't need to know in advance how long you want the sequence to be. So to make these long bad sequences, I use two tricks. So unbounded start and unbounded increase, but this does not happen in my algorithm, because the runs, so in broadcast protocol, I don't have unbounded increases. You know, the size of the configuration will at most increase by 1 if there is a spawn step. And the starting configuration, well, it's the input of my problem, so it's given to me. So the way we can capture this is by looking at controlled sequence, so sequences that do not grow too fast. And my definition of a controlled sequence is a sequence such that the ith element has size at most j of j of j of n0. So you give me n0 and j, and this will be the control. So this will give me the definition of control functions. So this is a parameter of a definition. So now, if I take a well-quasi-ordering with some notion of size of elements, if I take a control pair, n0 and g, now there is a maximum length of for all bad sequences that are controlled. And this is because with this n0, the set of all sequences, so if I arrange this in a forest, there is only finitely many starting points. And because of this g, the branching will be finite. The branching of the forest will be finite. And you look at the maximal branch and its length, you write it this way. So it's a function with 3 arguments, but usually g and a are fixed, and n0 is your input. And we have such kind of what we call length function theorem. So we can bound this this function, so Lg in nk, by g prime k. So g prime is some variation on g. So you have to modify g to have the proof. And this k subscript is the same subscript that I use when I said the f alpha, so it means iterated k times. And what is important in the end, if you tell me that j is in this class, so I don't need to know j precisely, I just need to know that j is in this class, then I know that the length function is in that class. And this will give me the upper bound I need for my algorithm. So applied to a broadcast protocol, the runs that I look at, they are controlled by size of initial configuration and the successor function, meaning that at most during one step the size can increase by 1. And I will get that if I look at broadcast protocol with k states, so the example I showed had 5 states, the bound will be in this class f4. And if the number of states is not fixed, if I'm running this verification program for any broadcast protocol, then I will have this bound. So Ackermann function will be the bound. So it matches what we've seen on the example. If I do not termination, but I look at the pseudo runs, the same analysis. This time, I look at the size of a target state, and again, when I go backward, the minimal pseudo run, they are bounded by the size of the minimal pseudo run is bounded by a successor of the size of my state. And this general situation, our model gives us the well-quasi-ordering, tell us how state can grow inside in one step. So usually I don't care really what is G. If you tell me that G is primitive recursive, I'm happy. I can bound the rest. And with this kind of length function theorem, I will have an upper bound for this, and I will get a bound for the two algorithms that I've shown. So very quickly, I will mention some for other well-quasi-ordering. So here, this is the ordering, you know, of words, sequences of letters, ordered by embedding. So this is Higman's lemma. This is this well-quasi-ordering. So the complexity will be in this class, so the length of bad sequences. So this is resolved by Adam Sichon, and then has been refined when you look at the size of the alphabet or things like that. So these examples, we use them. I did not introduce them, so you don't know what are these time dark Petri net, but it's a model for distributed protocols where there is a real-time element in the protocol. So it's even more complex, as you can see here. And when I look at the priority ordering, now I have to go to F epsilon node. So I'm told that this is all functions that are provable in Peano arithmetic. I don't realize how big this is and what is next, but we can put a cap on the complexity of the system. So in this line of work, the research goal is to look at, you know, other well-quasi-ordering for which we don't know the complexity upper bound. So typically, for example, I mentioned this kind of power set because we have upper bound for multisets, but they are larger than what is needed. And when you look at in the literature, the maximal of order type of power set of well-quasi-ordering has not been analyzed, and we don't know precisely how to measure its size. Also, when you look at graph, well, the complexity of embedding of graph is very, very high, but in application, it's not all graphs all finite graphs that we're interested. It will be, let's say, graph without a cycle or other kind of graph. And I mentioned this, so I have no example here, but the two algorithms I've shown, it's very clear where the bad sequence occurs. Sometimes the algorithm are more nesting, and why it terminates because of a bad sequence, this is hidden. So the G function now is not so clear in this case. So for lower bound, I will just say that all the lower upper bound that are mentioned, so I will just mention this, all the lower bound that upper bound that I've mentioned are met by matching lower bounds. That is to say, the models have shown they need this kind of complexity. There is no smart method to do better in general. Of course, in any specific case, there can be a smart method, but in general, there is no better method. And the way to do this is to use this model to compute. The way to prove this is to use this model to compute the fast-growing function f alpha up to some alpha and their inverse. So it's when we saw with the broadcast protocol, I showed how it could compute tower. So this is this kind of thing that we have to do, but for higher functions, and also we have to do the inverse of the f alpha, so functions that take huge numbers and shrink them, and this has to be done in a correct way. So this is a kind of a construction that we need to prove lower bound, and for each model you need to prove it, because you don't know, there could be the upper bound could be very naive and not met in practice. So I will stop here, and I see that the time is finished for me, and I thank you for your attention.
Invite questions. I have a question. You mentioned power sets. It made me wonder, because there are better quasi-orderings.
Yeah.
Do they come in at all?
So, what did I mention?
Just now, you were saying
Yeah.
future research.
Yeah.
mentioned
So,
power sets.
okay. Here it was mentioned. So, better quasi-ordering, they occur in that. So we need to. So we have some data structure that is present in our models, and we need to prove that it's a well-quasi-ordering. And this data structure, they can be, so it's typical in computer programming. They are built by assembling a smaller element and combining them this way. And then, so if you look in model theory, it will be, you take some algebras, you glue them, and then you restrict, and we need to know that the result can be partially ordered by this ordering. And how do we know that? Is by using typical generic construction like Kruskal tree theorem or things like that. And sometimes, in order to apply, they need the ordering to be not just a well-quasi-ordering, but a better quasi-ordering. So sometimes we need to know that. Here we just borrow result from the literature. We don't try to develop new ones. Yes. So for example, power set. So it depends what kind of ordering. Here I was talking about finite power set.
Yes.
So with embedding, it will be well quasi-ordered. But sometimes we're interested sometimes in infinite power set, sometimes in the reverse ordering. This. So it can occur that we need to know that the elements of the power set are better quasi-ordered.
I think in the beginning you mentioned the graph minor theorem. So did you ever, or is there any example where one uses the well-quasi-ordering of finite graphs? And if, what kind of, do you use a subclass of graphs?
So I've seen it used by some colleagues who were doing. So they were modeling configuration of their system by graphs, and one step would be described by some graph rewriting. And they would have this kind of monotonicity that if a graph contains a smaller one, and the smaller one can do this step, then the bigger one can do a similar step. I can't tell you if they were restricted to subclass of graphs.
Planar graphs or something like
So Sylvain, maybe you know better, or?
In those examples, sometimes they have the full class of graphs, but they assume that the system is somehow lossy again, like this priority channel system, so that it can go to a minor, and then they use the graph minor. And other times they look at restricted classes of graphs with embedding, for instance. So if you don't have path of, if all the minimal path in the graph are on the length, then
so bounded version.
And sometimes also by when you restrict to a subclass of graphs, you can take an ordering that is stricter than a minor, like induced subgraph. Sometimes will be a well-quasi-ordering, of course, for restricted classes of graph. And again, what is the complexity, or what is the type of this ordering? This is thing that will have impact on the complexity. I cannot tell you what application they have because I've not looked at this in details.
Let us thank our speaker again. Coffee is